Hello everyone, welcome to LogicTronix Webinar Series 2022. We are here at LogicTronix ADAS Webinar. It's Krishna from LogicTronix. Thanks for joining this webinar again. And in this webinar session, we are going to have in-depth session on ADAS technologies. Mainly we'll be deep diving on sensor fusion, how we can fuse multiple interface of camera sensors like GMSL, FPD, MIPI, IES, etc. and how we can integrate LiDAR, radar and ultrasound is multiple sensors, and we'll also be going through running the machine learning workload over the fuse sensor inputs so that we can have the feature extracted from each sensor and we can process it according to the requirement, and we can also actuate the necessary decision making element of vehicle. We are also going through the LogicTronix ADAS reference design. We already have released LogicTronix ADAS 1.0, which consists of 4 GMSL camera link as well as 8 ultrasound for replicating the complete ADAS system, and this reference design is available for evaluation and testing, targeted for Xilinx MIPI SoC platform. And after this reference design, we'll be jumping to the Q&A, which will be live Q&A. We'll be covering your live queries and we'll also be responding your queries over the email. Without further ado, I would like to pass my colleague Nikhil for the ADAS brief technologies, sensor fusion on the ADAS. So he'll be deep diving you all on this section, and on the machine learning acceleration for ADAS, I will be rejoining this webinar and we'll be continuing from there. So Nikhil, you can go on the deep diving of ADAS technologies and sensor fusion.
Thank you, Krishna. Hello everyone, this is Nikhil Thapa. I am FPGA Computer Vision Design Lead Engineer at LogicTronix. Today we are going to have a webinar on ADAS Driver Assistance System, or ADAS. I will cover ADAS overview, level of vehicle autonomy, vehicle hardware, ADAS sensor fusion, and LogicTronix reference design on ADAS. Okay, let's begin. ADAS, as we all know, stands for Advanced Driver Assistance System. The system is highly popular in automobile industry. The system has a major functionality in that it assists driver in order to avoid accident and provide road safety. The following features are illustrating the ADAS, such as camera and ultrasonic sensor field of view for covering the surrounding of the vehicle and possible object detection. ADAS can have multiple set of cameras and sensor interface to grab the surrounding information of the vehicle. Information is supplied to ECU, that is Electronic Control Unit, which is the main processing unit here. ECU is further interfaced with the peripherals and display and touch unit to control peripherals, or to show the status through display unit, or to take user touch input to do user-oriented control. In a nutshell, the ADAS is the group of electronics technologies creating a human-machine interface, or HMI, in the field of automobile industry for road safety. Many cars vendors such as Tesla, Mercedes, Bosch, Audi, etc. are chasing after ADAS and ultimately towards autonomous driving. The traditional ADAS did not have deep learning capabilities, so were no intelligent compared to modern ADAS system. Therefore, auto driving were almost impossible. On the right hand side, you can see the block diagrammatic view of traditional ADAS system. The traditional ADAS system was only the first step. Now it can be taken to the next level by introducing machine learning capability. It could become the ultimate gateway towards the futuristic, artificially intelligent autonomous driving system, where the vehicle would drive itself without the requirements of driver. Due to AI and sensor fusion, ADAS can precisely detect, correct, and recognize things around the car. The essential safety-critical ADAS applications include pedestrian detection, lane departure warning, traffic sign recognition, automatic emergency braking, blind spot detection. On the right hand side, you can see the block diagrammatic view of ML-based ADAS system with the sensor fusion on Zinc UltraScale Plus MP SoC. Here we talk about the different levels to become vehicle from manual control to fully autonomous. The Society of Automotive Engineers, also called SAE, has developed a convenient 5 levels nomenclature to define the different levels of autonomy. If level 0 is not considered, then there will be only 5 levels. The level 1 and 2 are doing the driver assisting role or function. That's why human involvement is still required and important. On the other hand, level 3, 4, and 5 will do the automatic driving function so that human interaction will not be required. Human can still override in level 3 and 4. For autonomous vehicle driving, the accurate vehicle surrounding information is so important that the machine learning and the sensor fusion will play a massive role in these levels. Let's look at a brief information of each individual levels. Okay, let's talk about hardware that are required for ADAS. The following are the highlighting hardware components for general ADAS system. Okay, we will go to have a brief familiarization with this hardware. Okay, let's go with the camera. Okay, it is the source of visual information and also important part of computer vision. It becomes the eyes of computer vision and also in the most ADAS system. The camera makes it possible to do varieties of visual interpretation such as image video processing to extract the feature of the scene. When ML capabilities are added, the camera system helps to achieve even more intelligent functions. There can be more numbers of camera configuration in a single ADAS system. Okay, at least 4 camera configuration will be sufficient to cover our 360-degree view. However, the camera installation and configuration generally depends on fulfilling the vehicle or situational requirements. The configuration can have a wide varieties from 4 numbers of camera to 8 or even higher. In ADAS, the camera has detection and recognition functions such as vehicle recognition or detection, pedestrian, traffic signs, and road markings, and color detection. There can be a wide variety of cameras types depending upon their capabilities and features. It can be from high resolution to high speed cameras. Some are commercial grade cameras and some are automotive grade. Sometimes it becomes a huge deal to choose the right one. However, automotive grade cameras are preferred. Okay, when we talk about camera itself, it has 2 terminologies to understand. Okay, that is camera module and camera sensor. When there is a camera sensor and its pre-processing circuit and some lens arrangement, it is called camera module. It has a defined interface to connect with other devices. The camera sensor means just a sensor in some microcircuits. The most common sensors are CMOS image sensor. The circuitry in the sensor is used to read and transfer the sensor data signal. The signaling standard used in most sensors is generally a differential signal. The many camera sensors use the low voltage differential signaling or LVDS standard. The pre-processing unit takes the LVDS data to do some early processing and then generates data in the form of common camera interfaces such as HDMI, MIPI, VGA, LB, CMOS, etc. You can notice a camera sensor always lies within a camera module. In an ADAS system, a camera module has a different story. That is, for interfacing, there are separate circuits. The circuit consists of high-speed serializing or deserializing ICs. The IC is capable of receiving various sensor signal formats, and the common format is LVDS, and generating serial data, which is also known as link output. The link will be interfaced with the receiving system. The receiving system has a corresponding deserializing counter ICs, meaning the serializing and deserializing ICs have a defined counterpart. The camera module may or may not consist of reprocessing unit. The serializing circuit is only providing an interface to camera and receiving device. Okay, in the field of ADAS, there are two popularly adopted data transfer methodologies. So they are the use of serializing and deserializing data techniques. So they use GMSL or FPD technology. When a camera uses GMSL serializer ICs, it is termed as a GMSL camera. And on the other hand, FPD cameras are those cameras who obviously employ FPD serializer ICs. So we will have a brief explanation of these IPs after this slide. And you can also check a similar thing on this picture. So ADAS camera, gigabit multimedia serial link, GMSL, CRDS ICs. Okay, these ICs are used for high-speed communication that fully supports the high bandwidth complex interconnect and data integrity requirements needed to support evolving automotive infotainment and ADAS. These ICs are made by Maxim Integrated. There are varieties of such ICs which have several different parameters. These circuits provide a high-speed camera link interface between a high-speed camera with high resolution and processing device. It can transfer a video up to 6 Gbps. The CRDS technique is very popular across telecommunication, data communication, industrial, and cable interconnect applications, as it offers high data rates, long distance support, and better performance. The primary use of a CRDS technique is to provide data transmission over a single coaxial cable or a differential paired cables such as standard twisted pair or SDP up to 15 meters to minimize the number of input and output pins and interconnects. Okay, this picture is illustration for the GMSL CRDS technology. At transmitting side, such as a camera, the parallel video data are serialized by GMSL serializer ICs, while at receiving side, the serial link is converted back into parallel video by deserializing IC. Okay, there are varieties of such ICs, and each IC has a corresponding serializing deserializing counterpart. Yeah, this picture has been taken from the Maxim Integrated product selection page, where you can find various CRDS ICs with different RxTX capabilities. Okay, apart from GMSL, there is also another standard which is mostly adopted by camera sensor interface. Okay, that is MIPI standard. This is predominantly used in mobile devices, as we all know. This standard also provides high resolution, high speed camera interfacing up to 6 Gbps. However, GMSL puts lots of merits over MIPI. Okay, let's find out by following points. The distance of transmission. The GMSL CRDS technology can be more helpful in enabling a long distance transmission up to a distance of 15 meters. So that means a camera can be placed 15 meters away from the host processor. On the other hand, the maximum cable length for a standard MIPI CSI2 camera connection is 30 cm. EMC performance. GMSL uses a differential signaling method for the link, which improves the electromagnetic interference or EMI performance. Maxim serializer ICs have a high immunity mode HIM, which provides more reliable reverse channel communication and also provides robust control channel electromagnetic compatibility tolerance than MIPI. And when we talk about automatic repeat request, that is ARQ, is an error control and packet recovery method which is employed in GMSL to ensure reliable data transmission. Okay, let's move into FPD, which is flat panel display SerDes ICs. Okay, on the other hand, a Texas Instrument TI also has developed its serializer and deserializer technology, which is commonly known as flat panel display FPD Link 3. The TI serializer ICs are capable of receiving input with data standard of LVCMOS, MIPI DSI, MIPI CSI2, SDMI, LVDS, FPD Link, and giving output data in the formats of FPD Link 3rd LVDS. Deserializer ICs are capable of receiving input data standard of FPD Link 3 LVDS and giving output data format in MIPI CSI2, LVDS, or LVCMOS. So like GMSL, FPD SerDes ICs also have their counterpart. The FPD ICs primarily are used for the high-speed data transfer between processing unit and display unit. However, ICs can be used between camera and processing unit too. Okay, following picture is an illustration for FPD SerDes technology. Okay, at the transmitting end is serializing the data through FPD serializing ICs, while receiving end is retrieving that information or the data by deserializing ICs. Okay, FPD technologies seem to be similar to GMSL. Both technologies are addressing same field. Either of ICs can be chosen for ADAS development. Just like GMSL SerDes ICs, there are a wide varieties of FPD ICs that can be found on TI product page. Okay, this table illustrates some of the GMSL and FPD cameras used in ADAS development. Here you can find. Okay, let's move to sensor. So sensor include LiDAR, radar, ultrasonic sensor. Okay, so a sensor, as we all know, is a device that is used to sense the condition. It consists of an underlying transducer that converts one form of energy into another form. The sensor have different designs that have wide application in a variety of fields. In the field of automobile industry, the mostly adopted sensors are LiDAR, radar, and ultrasonic or sonar sensors. Let's have a brief information about the sensor. Okay, LiDAR, it stands for light detection and ranging. As the name says, it uses light, which is typically laser light. The sensor technology uses beam of laser light to measure several ranges around it. These ranges form numbers of points that can be utilized to make a 3D world around it. The sensor is widely going to be used in the automobile industry to plot a digital 3D map around a vehicle for the sake of ADAS. LiDAR provides better accuracy than radar. For the connectivity, this type of sensor implements Ethernet interface. The Velodyne LiDAR has 100 Mbps Ethernet interface to transfer its data to processing unit. Okay, so when we talk about its working mechanism, LiDAR has a transceiver which has a transmitter, receiver, and timing measurement unit. The transmitter unit consists of light source, which is laser light source, and optical system. The optical system consists of some lens arrangement to guide the outgoing laser beam. Similarly, the receiver unit consists of a photosensor and optical system. Generally, photodiodes are used for receiving the reflected beam. Like the transmitter unit, the receiver unit has the optical system, which again consists of some lens arrangement to properly guide the reflected beam towards the photosensor. The following picture illustrates a functional block diagrammatic view of LiDAR working mechanism. Okay, the timing measurement unit has the time measuring circuitry which initiates the signal for the transmission of laser beam and then counts the time of flight until transmitted signal is received after the reflection from the object. So when we know speed of light and time of flight, then obviously d can be calculated. Okay, here d means a distance. Okay, so when multiple light beams are used, each ray can have a separate time of flight and separate range or distance. When all corresponding distances are plotted, it forms a point cloud and it gives a 3D surrounding view around the sensor. Okay, here we can find one of the LiDAR specification. Okay, this is the Velodyne BLP-16 LiDAR specification. Here we can find a different sensor specification, mechanical, electrical, or operational specification, output specification. Okay, you can find a similar specification on the Velodyne product page. Okay, here are some top LiDAR companies. We can visit their product page to get good information about their LiDAR product. Okay, let's go to radar. It stands for radio detection and ranging, which uses radio waves of certain frequency in the order of megahertz to gigahertz to measure the ranges. It can give a very long range distance measurement. In ADAS, radar is used for measurement of gappings between the vehicles and also measuring the relative speed to avoid potential collision. There is also a wide variety of ADAS radar sensors to choose for ADAS purpose. Okay, there are some radar companies which produce automotive grade radar sensor. We can visit their product page to have more detailed information. Okay, here is Ultrasonic Sensor, which is one of the common sensor in the market. There are a wide variety of ultrasonic sensors. However, their principal working mechanism are similar, but their field of application are a little different because sensor precision and range accuracy are different. These sensors are used to detect the object by measuring the range between the sensor and the target object. It is mostly used in a car parking system and also in a parking management system. Okay, when we talk about its working mechanism, okay, it generally uses ultrasound wave burst of order 40 to 48 kilohertz. It uses a time of flight calculation to measure the distance or range. The processing engine, that is PE, uses echo-pulse duration to calculate the distance. Ultrasonic sensors are primarily used for proximity sensing rather than range measurement. The sensor can measure the minimum distance of 15 to 20 centimeter and maximum distance of 4 to 5 meter. Okay, let's move to processing engine. The processing engine can be anything such as a computer, GPU, microprocessor, microcontroller, or FPGA devices that can take a data input, process it, and generate the data output. For ADAS, the automotive grade processing engine are used. There are two most popular embedded system design platform in the market. They are GPU and FPGA. They have head-to-head competition because of user-friendly, cost, power, design flexibility, and performance. When we talk about FPGA devices, their uses and applications are rapidly spreading over automobile field. The most preferable FPGA devices that are used in ADAS are SoC and MIPI SoC. The AMD Xilinx, which was formerly Xilinx, primarily has produced several ADAS automotive grade FPGA chips, okay, which are primarily targeted for ADAS, okay. So they are Xilinx automotive grade Zinc 7000 SoCs, and the Xilinx automotive grade UltraScale Plus MPI SoCs. The MPI SoC FPGAs have a huge capabilities for data handling and data processing for ADAS. Okay, let's find out why FPGA is rapidly emerging in an ADAS field against GPU. Here are a few points that highlight the FPGA capabilities over GPU. FPGAs have higher compute capability compared to GPU, okay, and the reconfigurability of FPGA provides the custom ADAS design testing and debugging faster and easier. When compared to same performance capable GPUs and FPGAs, the GPUs are the most power hungry devices for their performance, while FPGAs are the most power efficient device well known so far. Okay, this is a very much important thing for battery operated system. The ADAS requires power efficient hardware. FPGAs can handle large volume of data with parallel processing. FPGA provides a large number of I/O pins to interface a wide variety of sensors and peripherals. FPGA also allows to create a customized ADAS dedicated processing hardware on its programmable logic with a dedicated software on PS side. The processing hardware can also be accelerated to enhance the existing FPGA performance furthermore. And the newly produced power and cost efficient MPI SoC FPGAs such as KB260, JC104 have incredible ML inference capabilities to get high FPS ML output. Okay, these are just a few points. However, there are more points we can consider. Okay, let's go to our peripherals. Okay, to control certain vehicle components such as the door, seat belt, steering wheel, wheel brake, mirror, wiper, headlights, turn indicators, parking lights, engine, power system, and etc. The ADAS can have peripheral units. The processing engine can generate the data that can be sent to peripheral units to control above-mentioned units of vehicle. For example, triggering emergency braking unit when objects detected in front of vehicle, and also adaptive cruise control by controlling the brake and acceleration and managing the power uses for the electric vehicle. So for this control action, the peripheral unit can have a motor driving unit, relay control unit, power control unit, and so on. The peripheral unit can also provide the feedback to processing engine to have better control. Okay, let's move to our display and touch unit. In the ADAS, the display and touch unit has both input and output capabilities that eventually form the human-machine interface, or HMI, through which a user take or give information to the system. The unit has a touch input capable display screen from where user can get all ADAS related visual, textual, and symbolic information. In the meantime, the user can give the command to switch and select between information and its status by touch input. The display and touch unit resides in the driver's deck, like in the Tesla car shown below. Okay, now we can check ADAS applications such as adaptive cruise control. That is, there will be automatic vehicle speed control by acceleration or deceleration or braking. Smart parking. Okay, it includes automatic parking with the utilization of rear view and surrounding view camera data. Emergency braking. Okay, the pre-collision information is utilized for emergency braking. Blind spot monitoring. The rear view and surrounding camera data can be utilized for blind spot object detection, monitoring, and generating the warning. Navigation. ADAS generates and provides instruction to driver to follow the route. The driver monitoring system. It consists of monitoring the status of driver, whether she or he is focused on or distracted from the driving, and generating the warning if distracted. Okay, light control. It includes changing the strength, direction, and rotation of lights depending on a vehicle's environment and darkness. So vehicle-to-vehicle communication. It includes vehicle-to-vehicle, or also called car-to-car communication, to exchange the ADAS information among the vehicles for early information of vehicle's action. Okay, now let's move into ADAS sensor fusion. So as we all know, different sensors for object detection have their advantages and disadvantages. Sensor fusion integrates different sensors for more accurate and robust detection. For instance, in object detection, the camera can provide a rich texture-based and color-based information, which LiDAR generally lacks. On the other hand, LiDAR can work in a low visibility, such as at night or in moderate fog or rain. The LiDAR can provide a much more accurate spatial coordinate estimation compared to camera. Okay, sensor fusion uses image recognition software, ultrasonic sensor, LiDAR, and radar to combine massive amounts of data in a manner similar to how the human brain processes information. So fusion can be done by two ways, that is data fusion, where sensor features are meshed and combined to each other. Output fusion, the processing sensor data separately, like detection, recognition, and fusing the individual results. Okay, the following table clearly explains why we need sensor fusion. You can find these advantages and their limitation by this table, and that's why you will be able to know why we should do LiDAR and camera fusion. Okay, let's look at it. Camera and LiDAR fusion in FPGA. It shows block diagrammatic view of top level fusion process, and it uses a data output fusion method. So here you can see the camera and LiDAR, and both of them are having a pre-processing, and their data are sent to the feature extraction network, and finally feature matching and integration network generates the combined output. The camera pre-processing will use the processing of raw pixel data and color conversion, auto white balance. Okay, and in case of LiDAR, it uses a compression, ground removable things processing in its pre-processing block. The compression is also done here for reducing the data volume to avoid bottleneck effect. The point pillar network is used to convert 3D projection into 2D form. And for the feature extraction network, a DPU core along with a Vitis AI will be used. Okay, for the camera feature detection, YOLO model will be used for the detection. And while in case of LiDAR, the several networks such as PointNet, VoxNet are used for feature extraction. And then finally, all the extracted outputs will be combined in a feature matching and integration network. And finally, we got the output like shown here. Okay, here it is, the Xilinx MPSoC. This is a functional view of a sensor fusion, for which a Xilinx MPSoC FPGA is considered for the design. Okay, it shows the PS and PL side of view. Okay, here you see the 4 cameras which sends data over GMSL or the FPD link. Okay, and to transfer this data into FPGA, a multi-camera FMC module is used. This FMC module will have a deserializer circuit which deserializes each individual camera data into a MIPI format, and that data is sent to FPGA by FMC connector. Okay, so in the programmable logic, you can see the capture pipeline, which consists of MIPI CSI2 RAX block, and subset converter, and stream switch. Here, stream switch is used to demultiplex 4 individual camera link. Okay, and each link will have a separate pre-processing pipeline. And finally, in case of LiDAR, the Ethernet interface will be used, as the LiDAR gives 100 Mbps Ethernet link, and all of the controlling configuration things will be done in the application. Okay, and the feature extraction thing will be done in a DPU, which you can see the machine learning pipeline in a programmable logic. Okay, and finally, application will combine all of the features from these two LiDAR and cameras into one. So for buffering all of the data, it will use the DDR memory. Okay, and finally, output will be sent to the output monitor through the DP controller. Here we can see the individual processing pipeline. Okay, now for the ADAS machine learning acceleration, I will hand these to Krishna.
Thanks, Nikhil, for passing me the floor. And hello everyone, it's Krishna again. And in this PowerPoint, we are having how we can create the complete machine learning acceleration flow on the Xilinx MPSoC platform. So first of all, we are going to have the Velodyne design or PyTis platform and overlay, including the Xilinx DPU IP core. And after having that, we can have the XSA generated from PyTis or Velodyne, and we'll be using that XSA for Linux build or Linux development. And the Linux image or weak image will be used for running a specific inference examples or AI workload on the MPSoC platform. So the second step after creating the hardware is like preparing the model. Either we can use the Xilinx PyTci Model 2 based models. There are like 130 plus trained model available over the PyTci Model 2. We can just use those model according to our DPU architecture. We can just compile those model, and for this example we are taking like 4 different model from PyTci Model 2, which is person detection, pedestrian detection, vehicle detection, and license plate detection. These models are available there at PyTci Model 2. We are using PyTci 1.3. So mainly this section covers on how we can prepare our model. So just preparing of model is depicted over here. And there is also LiDAR point cloud based classification model available on PyTci 1.3. So we are also targeting that model for LiDAR based ML workload. So there is 2 ML based workload we are targeting on this flow. One is for camera stream based ML workload or camera stream based neural network. Another is LiDAR point cloud based classification and segmentation workload or network. And another part, third part on ML acceleration is inferencing. So we have to either write the inference script on CPP or the Python. We can use any of them. After running the Linux boot image on MPSoC board, we have to install the PyTci, and after PyTci install, we can run our custom model from the second step. That is, we will be getting like X model from compilation. So that X model can be run over this third inference step. So we'll be using X model along with C++ or Python application. So we can use any of the application, inference application, and this inference application we are targeting is going to like run the DPU and run the train model X model over the DPU and create the like bounding box information. That bounding box information is going to process by MPSoC processing system or PS, and it will be created like any labels and the counting information and detection of a specific bounding box on the given stream. So this is just one pipeline, and we can run that specific pipeline with the GStreamer. So GStreamer is also supported by the Linux based framework, Linux based development environment, and there is also another way of using GStreamer, which is we're using this BBAS. And on this example, we are just targeting the Linux GStreamer interface. And the last one is the UI or say HMI interface. So as we are developing complete Linux system, so we are targeting Qt based UI interface, Qt based UI based UI development plans. So we will also be showing you LogicTronix ADAS 1.0 example design, reference design, which we also have included the UI. So UI is mainly for like flat panel display based user interface, so that driver can get information about what's going on, and either any vehicle behind or front, or any pedestrian is detected, or any like alarm is generated by the ultrasound sensor, or any information generated by other LiDAR or radar sensor can be presented on the HMI or GUI. So this is mainly for assisting the driver. So yeah, this is the machine learning acceleration side. And regarding to ByteCI model 2, we can use different models from ByteCI 1.3, and if we go for ByteCI 2.0, there is more larger number of trained models which can be easily used for Xilinx MIPI SoC platform or Linux based image. So we are just listing like 3 different models. One is for radar, 4D radar, another is LiDAR, and another is also LiDAR fusion 3D detection. And we can also run like BART based examples for basic ADAS implementation, which consists of like segmentation type of examples. And there is also ByteCI library, which consists of number of inference scripts in C++, which can also be used for like point pillars segmentation with 3D and plate detection, etc. So this is the general ML acceleration flow. And we can now jump to the LogicTronix FPGA ADAS 1.0 reference design. So Nikhil will be much more describing this reference design. This consists of 4 different camera streams from GMSL and with 8 ultrasound. So Nikhil, you can again continue the session.
Okay, thank you, Krishna. We LogicTronix also have made FPGA ADAS reference design. It consists of following. So here you can see the brief general overview, and which consists of a brief ML-based reference design for ADAS solution. It uses Zinc UltraScale Plus MIPI SoC device. The necessary hardware are Quad AR023180 camera FMC bundle. Actually, this bundle consists of the 4 cameras and their FMC. The camera has serializing ICs, while FMC has a deserializing ICs. Okay, and it uses an Ultra Z EB carrier board, and for which, so we will use Ultra Z EZ or EBSOM. The tools used for this design are Vivado 2020.2 or later version can be used, and the Linux version 2020.2 and ByteCI 1.3.1. Okay, let's understand its flow. The camera feeds can be captured and done the post-processing by the capture pipeline. Okay, and the proximity distance calculated by the ultrasonic distance calculation pipeline. The machine learning pipeline can implement AI to detect and recognize the objects such as vehicle road markings, traffic markings, vehicle number plates, obstacles, etc. This display pipeline can utilize the ML pipeline information and do the video and audio composition, such as emphasizing the recognized object by bounding box and showing other scenery details in the display unit. To host and extend the functionality and operability of such system, application can be written. Okay, here you see a full functional view of the design, and it again shows the PL part and PS part. Okay, in the PL part we will have ultrasonic distance calculation pipeline, capture pipeline, machine learning pipeline, display pipeline, while in the processing side we will have application running over ARM cortex, or also say application processor unit. Okay, ultrasonic distance pipeline. Okay, it has 8 individual distance calculus and IP cores, and they are responsible for triggering the ultrasonic pulse and also receiving echoes from the sensors. And the trigger pulses are generated every regular interval, which is here designed to be in a 50 millisecond. And then based on receiving the echo pulse, the IP core calculates the distance in centimeter. And the distance value is stored in IP register. Okay, so there will be 8 register for 8 distance calculus and IP core, and this register value will be read from the application side through XGP. Okay, and this value will be utilized to show whether warning or not. Okay, here it is, the capture pipeline. The pipeline is responsible for receiving the camera data, pre-processing data, and writing data into the memory. The pipeline consists of a series of blocks, namely a MIPI CSI2RX subset converter, stream switch, and pre-processing pipeline block. The camera data are obtained into FPGA by MIPI CSI2 data format. These data are processed by MIPI CSI2RX blocks, which then generates access stream. The stream data with conversion is performed by a subset converter block. This block generates proper stream width for upcoming processing blocks. The stream switch block is used to demultiplex a single stream into 4 individual streams. And now its stream of data goes to 4 pre-processing pipeline blocks respectively. The pre-processing pipeline consists of a pair to RGB converter, color space converter, scaling, and buffer write IP blocks. The pair to RGB converter converts the raw format of sensor data into RGB format. The color space converter block can convert RGB data format into other formats such as YUV. The scaling block can do the scaling incoming video resolution into different output resolution. The scalar resolution will be utilized in the ML pipeline as well as in the display pipeline. Actually, the DPU requires the stream size in 640 by 480, for which scaling will be used. The buffer write block is used to write the data into 4 separate locations of DDR memory with a specific color format and resolution value. This memory location will be accessed by the ML pipeline to retrieve the camera data and do the ML tasks. Okay, this design is following Vivado flow, which means DPU IP block will already be present in Vivado hardware block design. This pipeline generally comes in between capture pipeline and display pipeline. This all depends on the type of design. The pipeline uses a DPU deep learning process, okay, which is also called this is a IP core, and upon which the convolutional neural network or CNN will be run. This core is programmable engine for deep neural networks. It is pre-implemented on the hardware with no place and route required. It allows the efficient implementation of many deep neural networks. Okay, and the DPU IP has slave port so that it can be programmed from the PS side, and also the master ports, which are used to access the memory location for input images as well as temporary output data. And in the reference design, a DPU core has a following major configuration, that is, numbers of core used is 1, architecture of DPU is B4096, and the RAM uses is set to low. Okay, in the design, DPU core accesses first input stream frame from the memory, and however, DPU can only take 640 by 480 resolution of frame, so the resolution is downscaled by the scaling IP block. The DPU core then does a task such as detection of a specific object in the frame, and information are utilized by the application running on APU to show markings in the front and the rear camera. This frame will become the final output, which is again stored in another memory location. So multitude of detection model can be run or implemented upon the DPU core. Okay, from the ADAS reference design point of view, the design will be able to do following things such as vehicle license plate recognition, vehicle to vehicle distancing, face detection, pedestrian detection, traffic sign detection, animal detection, and so on. And let's move into our display pipeline. This pipeline contributes to showing off the processed camera data on the display monitor. The video mixing block is the major block of this pipeline, which will read the ML processed data from the memory and show them as overlay layers. The resulting video data is converted into parallel data by access to video out IP block. This block takes the stream data and video timing as input and generates parallel video data. This data will be fed to live display interface, that is live display port, which is termed as DP interface. Okay, let's move into its application design. Before starting application design, the hardware file is generated from the Vivado and will be used for Linux application. It will be used the following steps to complete the application design. So first we use Ultrajet BSP, then configure device tree, build Linux, and run the SD card image. And here we provide the Linux user application where we read the ultrasonic sensor distance register and also run the JStream pipeline. Okay, the 4 detection network will be run upon 4 camera stream using following JStreamer pipeline. The pedestrian detection, license plate recognition, car detection network will be run. Okay, here we see a human machine interface. So after data outcome from the PL processing pipeline, the data are utilized to display in display unit such as flat panel display. The lightweight GUI developed on Qt framework will be displayed in the FPD, where all 4 camera data with the detection information will be displayed using GStream pipeline. The FPD creates the human machine interface from which user can get information as well as user can enter the information. On the other hand, the detection information can also be delivered to user by visual color signs and text signaling. Okay, GUI has 4 sections for front camera feed, back camera feed, information section, and pre-crash detection info section. The pedestrian detection will be shown in the front camera feed section. Vehicle number plate detection will be shown in back camera feed section. The crash information will be shown in the pre-crash detection information section. Front and rear camera detection and ultrasonic sensor information will be shown in information section. Okay, following picture shows the entire hardware setup connection. Here you see there are 4 cameras which are connected by coaxial cable to the Ethernet FMC quad cam module. Okay, it has deserializer ICs, and it has a FMC connector which will be connected to Ultrajet carrier board FMC connector head, and thus camera stream will be sent to the programmable logic of this device. And there will be Ultrajet SOM. Okay, so all of the things, processing part and programmable logic part will be here. Okay, all the implementation will be done here. And finally, display port will be used to connect all of the output to flat panel display. Okay, the figure shows here the 4 camera setup and installation, and also it shows the ultrasonic sensor fitting. Okay, and the camera are installed in such a way that the front camera is used for pedestrian detection, back camera is used for back vehicle number plate detection, and the left right cameras are used for pre-crash detection. And 4 ultrasonics are attached to front bumper of the car to detect front objects, while 4 other ultrasonic sensors are attached to rear bumper of car to detect rear objects. Okay, now, so what will be the next after this ADAS solution? So this current version, which is ADAS 1.0, is only based on 4 camera and 4 camera front and rear ultrasonic sensor inputs. The next version, ADAS 2.0, will have sensor fusion such as LiDAR, ultrasonic sensor, along with 8 numbers of cameras to expand ADAS system capability and feature to greater extent. And here are also ADAS 2.0 featuring hardware implementation. Okay, we will have a custom ADAS capable MIPI SoC FPGA SOM carrier board, and we will also have Kriya ROS board hardware implementation. The boards will have pre-built interfaces for GMSL cameras, ultrasonic sensor, and LiDAR sensor. So both of the implementation will use PETA Linux and Vitis overlay methodologies. Okay, here is the early demo of ADAS 2.0. And thank you all guys for having this webinar. All together, we'll meet you in other webinars. Okay, now I hand over this to Krishna.
Thanks, Nikhil, again for the in-depth session and detailing the LogicTronix ADAS 1.0 as well as what's coming up on ADAS 2.0 and going through the preview of a demo of ADAS 2.0. Okay, everyone, thanks again for joining this session, and we are just here at Q&A. So we'll be taking few queries at this session, as this session is already quite long. So just revising some of the questions which we have got. So some questions are from like, can we have any MPSoC board for this ADAS deployment or ADAS based implementation? This is the question, and just answering that, yeah, we can use any of MPSoC, and the best best platform is EG or EV device. And for EV device, we can also use the encoding and video decoding if needed, but not encoding or decoding video is needed all the time. EG can be the most suitable spot or suitable device. This is the one question, and thanks for the question again. And another question is like, what type of models which we can run on like LiDAR. So at the moment, LiDAR processing or say pre-processing and ML inferencing with LiDAR data is quite interesting and quite new also. So Xilinx also have released like 2 or 3 different models for point pillars and LiDAR based processing and ML workload. So you can also go through the PyDCI 2.0 and check, and the LiDAR based ML inferencing examples are available since PyDCI 1.3.1. so there are also some examples. And for inferencing, you can also join Xilinx developer.xilinx.com, so where you can see complete example of how we can run the LiDAR based example on MPSoC platform. So this MPSoC design can also be customized for different MPSoC boards, not only for the specific given board, which we can convert to like a Kriya board or say other like 104, 102 or 106 CCU board. So yeah, this is the another question which we have. And we also have one more question we'll be taking on is on LogicTronix ADAS 2.0. So yeah, we have 2 things we are planning to release on. So this is Nikhil went through. LogicTronix ADAS 2.0 will be available on Kriya platform with ROS. So that will be running Ubuntu Linux top with ROS, and we'll be using LiDAR and all the GMSL camera links and the ultrasound. and this will be completely like ROS based platform, robot operating system based platform. And this is the one flow which we are going to release. Another is the generic PyTis and Linux flow based platform, which will not run any like additional layer of OS like ROS, which will run only the Linux. So the insights or core will be the same. The ROS is much more flexible in terms of like integrating LiDAR. So there is already support for Velodyne LiDAR with the ROS. So for Linux, we'll be tuning up or operating some of the drivers for LiDAR. So yeah, this is the top most questions which we have on this webinar. So furthermore queries we are going to handle over the email. So thanks everyone for joining this session. So this session is quite longer. So thanks for joining, and I will also thank my colleague Nikhil for deep diving all these sessions on ADAS, sensor fusion, and different type of sensors and capabilities, and detailing through the reference design, LogicTronix ADAS reference design. So yeah, thank you everyone, and if you got any queries, you can also write us at info@logictronix.com, and we'll be releasing ADAS 2.0 very soon, so you can keep in touch with us, and if you have any queries, you can just write us. Thank you everyone for joining this session, and yeah, meet you on next webinar. Thank you.